In this video, I want to help you review the concept of stress that you learned in your Strength of Materials class. I want to help you wrap your mind around what stress means. Consider a person lying on a bed of nails. I actually do this on occasion at science assemblies in local elementary schools. I sandwich myself between two beds of nails and have the principal stand on top of me. The little children in the front row are always covering their eyes, thinking they're going to see blood squirting out. But of course, nothing happens, and I'm really under no pain at all. Understanding the concept of stress will help you understand why I don't feel any pain when I'm sandwiched between these two beds of nails. Would it be valuable to find out how much weight was on each nail? Sure it would. If the principal standing on top weighs 200 pounds, and if there were only 20 nails, that would mean that there were 10 pounds per nail, or 10 pounds trying to push each nail into my body, and that would hurt. What if the principal's 200 pounds of weight were divided across 200 nails instead of just 20 nails? Well, that would result in only 1 pound of force trying to push each nail into my body, and that might still hurt. But what if the principal's 200-pound weight was divided across 2,000 nails? That would result in only 1/10 of a pound trying to push each nail into my body, and of course that wouldn't hurt at all. I hope you realize that the concept of stress is just taking a force and figuring out how that force has been distributed through the material, just like the principal's weight has been distributed across all 2,000 nails. There are two types of stress that can develop inside of a material. Normal stress, of course, which is designated with the Greek letter sigma. We draw that on a little speck of material 90 degrees to the face. That's what the word normal means, 90 degrees to. So we could draw it 90 degrees to this face. We'd call that sigma y. Or 90 degrees to this face. We'd call that sigma x. The second type of stress is shear stress, designated with the Greek letter tau, and that is a stress that's parallel to the face. So we draw that in this direction. We call it tau xy, because it's on the x face of the little element in the y direction. If we have stress on the right face upward, we'd have to have stress on the left face going downward, and we'd have to have stress on the top and bottom faces in these directions to balance the element. Now let's talk about different causes of these two types of stress. Axial stress is the cause that we spoke of earlier in this video. We compute it by taking the force divided by the cross-sectional area. For instance, if I have this beam and I pull on the end of the beam in this direction, if I were to look at an element of material on the top, I would see that it would have normal stress that could be calculated by the force divided by the cross-sectional area of the beam. The element in the middle of the beam would have the exact same stress on it, force divided by area. And the element on the bottom of the beam would also have the exact same stress, force divided by area. So axial forces are the same across the entire cross-section. Another cause of normal stress is bending. We compute that by taking mc divided by I. If I were to load this beam from the top, we would find that the beam would bend. And intuitively, we know that the bottom fiber would be then in tension and the top fibers would be in compression. So this top fiber here, we could show the stress on it as being in compression because of the bending. We'd calculate that stress using mc divided by I. The element of material in the center of the beam would have no normal stress, and the element on the bottom of the beam would have tensile stress equal to the mc divided by I. So the bottom of the beam and the top of the beam would have the same magnitude of stress. One would be in tension on the bottom and the other compression on the top. Now let's talk about causes of shear stress. The first one we'll address is average shear stress. What if a member were pulled in this direction? We could look at it like this and see what's going on in the bolt. These forces would put shear stress in that area of the bolt. We could calculate the shear stress on that area of the bolt using the force over area, V divided by A. And we call this single shear. We could also load something like this. If we look closely, we would notice that the force is actually trying to shear this area and this area. We could calculate the shear stress as the force divided by two areas. We call that double shear. Another cause of shear stress is called transverse shear stress. We calculate that using VQ divided by IT. we find that in a beam that's loaded like this, the top fiber has no transverse shear stress. The bottom fiber has no transverse shear stress. But the center has the maximum amount of shear stress. And we're going to compare the center fiber just left of the load with the center fiber just right of the load. First of all, let's look at the center element of metal just left of the load. The reaction force here at point A would try and shear the part of the beam upward like this. So the element would have a shear stress upward on the left side equal to VQ over IT. And the V, or the shear force in that equation, would be equal to the reaction force there, or the force that's trying to cause it to shear. And because it's up on the left-hand face, there must also be a corresponding shear stress down on the right-hand face, as well as stresses in these directions on the top and bottom faces. What about the element in the center of the beam, but just to the right side of the load? Well, the reaction force By is trying to shear this part of the beam, and so this element would have a shear stress upward on the right-hand face, where the V in the VQ over IT equation would be equal to the reaction force at B. And of course we'd have to have a shear stress on this side as well as on the top and bottom to balance that element. The third cause of shear stress is torsion. We calculate that with the equation Tc over J. Here's an example. If I were to load this beam in this direction, it would twist, causing torsion, and the elements around the outside of the beam would experience the maximum shear stress due to torsion, while the elements in the center would experience no shear stress. For instance, this element on the outside perimeter would experience maximum torsion, and we would draw it this direction and calculate it with Tc over J. And because there's shear stress on that face, there must also be an opposite shear stress on this face, and shear stresses in this direction along the top and bottom. We could also look at an element here on top. This element is also around the outside perimeter and would experience maximum torsional stress as well. We could draw the stress on this element with the tau stress going down on the right-hand face, calculated by Tc over J, with of course stresses in these directions on the other face to balance the element. Now let's summarize these two types of stresses. Normal stress is designated with the Greek letter sigma. Shear stress is designated with the Greek letter tau. Normal stress can be caused by axial loads. We calculate the stress due to those by the equation F over A. Bending also causes normal stress, and we calculate that using the equation mc over I. Shear stress can be caused by average shear stress. We calculate that by V over A, or V over 2A if it happens to be double shear. Shear stress is also caused by transverse shear, which is calculated using the equation VQ divided by IT. Shear stress is also caused by torsion, and we calculate that using the equation Tc divided by J. Which of all these stresses are worse? If we have a complex loading condition on a beam, we don't want to have to calculate the stress in every element in the beam. So it would be wise for us to understand which stresses are worse so that we can look at those areas and ignore the other areas that would clearly not be so bad. Bending and torsion are usually much higher than the other stresses since they are caused by moments or leverage. For instance, we looked at this beam and we noticed that the bottom fiber was in tension, a normal stress, and we could calculate that using mc divided by I. If we drew a free body diagram of this, we'd recognize that there was a reaction force here at a distance d, and that would have to be resisted by an internal moment at this point that we'd call m, and that would be equal to the force times the distance. So that moment is caused by the leverage of the reaction force at B, and we'd use that moment as the term m in this equation. And that, of course, is much worse than an F over A kind of equation, the force divided across an area. But the mc over I equation, m is actually a force at a leverage distance, so that is usually much worse. If we think about torsion, that is also a leverage-based stress. This element right here would have shear stress caused by the Tc over J, T being a force at a leverage distance. This force at this leverage distance causing the torque. So that is clearly worse than the VQ over IT or the V over A, because the V is not at a leverage distance, whereas the torsional shear stress is caused by a force at a leverage distance. So typically, the normal stress caused by bending or the shear stress caused by torsion are worse than the other types. So if we have a mechanism that's loaded in a complex way, we can look where the normal stress due to bending or the shear stress due to torsion are the worst. I hope this discussion has helped you review and wrap your mind around the concept of stress.